So just a comment on what takes so long when solving Gaussian elimination if you attempted to do that. First of all, so let's just quickly take a look at the code, which I still hope is somewhere. I'm just going to start a new Jupyter notebook. So we think computers are fast, and for a lot of applications they are. However, every multiplication, addition, walking through an array of numbers or doing something with them, it does take time. So the way these are typically counted as operation is sort of there is a single amount of, like there's amount of time that your computer takes to do a so-called floating point operation. So often the speed of a processor or something like that is measured in floating point operations per second, FPS. So a lot of times when you have the processor speed as 2.3 gigahertz, it's the number of operations, floating point operations per second. Okay? So 2.3 gigahertz, hertz is 1 over second, right? Means 2.3 billion operations per second. So as you start, and it looks a lot, right? Until it doesn't. So it all depends. It all depends what is the size of the problem that you're trying to solve. So there's floating point operations, but there's also access to the memory. Okay? So I have to, and I like visualizing, and you had that visual from me already, of a little librarian going to a bookshelf, right, and grabbing a book. Well, that's what you do when you're retrieving the information from memory. You go somewhere on a bookshelf, virtual bookshelf in the memory, and you're retrieving that book. And you know, taking that book from the shelf can take time. Right? And then you do something with those books, and then you put them back. Right? So this do something is this floating point operations, and then you're storing on some other bookshelf. Now, if your bookshelf, you know, is your bookshelf in Peri Castañeda library, or is your bookshelf in our physics, math, astronomy library? That's the closest one to us right now. Okay? So basically, that matters. Like, you know, it's going to take you 10 minutes to walk to RLF building, or it's going to take you almost 20 minutes to PCL. Okay? There is, now in computer time, that's not in minutes, but it is a finite amount of time that you need to actually go and retrieve or put things into the permanent memory that is not the working memory of the computer. So those are the things that take time. Now we're not going to go into details of analyzing. Numerical analysis does analyze how fast are the algorithms. Okay? But I do want to mention it just to give you an idea where the time is, and we're going to actually look into the algorithm today, LU decomposition, that saves some of the time. So it's a great introduction to that. So let me just quickly go to the code and show you the code and quickly show you how do you count the time taken. Where's my lectures? And then if I remember correctly, I have put my Python notebook somewhere in here in the wrong position, but nevertheless. There we go. So basically, if I look at my Gaussian elimination, I'm going to scroll down to my Gaussian elimination code, which is pretty much where is the final part of it, creating a function. Here we go. Okay. So this is where the time actually is. So I have two for loops, and technically first one will execute n times, where n is the size of my linear size of my matrix. So I have a matrix n. And then for every for loop here, I have another for loop. Okay, that is not there precisely n times, okay, but so I'm decreasing as I go along. So every time, so if I have n, then I have n minus 1 below me, right? So it's essentially sum of the n's and n minus 1s here for every, okay? So you can sum this up. You can do these sums. And then within these for loops, let's say that this is just a double for loop that executes n times, right? So n squared, if I'm traversing the entire matrix. Then inside here, I have one division to compute C. I have multiplication here, and this is done for the entire row. So there's n elements here. So n multiplications, n additions, and then one more multiplication and division, and addition. Okay? So this is 1, 2, 3 times n plus one more. So something like 3 times n plus 3 floating point operations. Does everybody see that around here? And again, I'm not being precise here, but you can literally count how many divisions or these floating point operations, which is addition and division, they take similar time, do here. So let's just assume, for the sake of the argument, that this is executed n times. It's less, slightly less, but it's n times. So I have n times n times 3n plus 3. Okay? So this is 3n cubed plus n, something like that. Yeah? N squared. The leading thing here, as my n becomes large, is n cubed. That's what's bothering me in terms of time. That's what dominates in that polynomial, right? So as n gets large in any polynomial, the largest power is what dominates. And we call that it's going to take O of n cubed operations. Algorithms that operate, and that's what dominating. Back substitution is on the order of O of n squared if I did the same count, okay? So it's one order less. So it's way faster, so it's not the one that is taking the most time. It's this actually forward eliminations that is expensive, okay? And we're not busy counting. It doesn't matter whether I have 4 or 5 multiplications if my computer does billions of those per second, right? It's not that big of a deal. But when I have larger and larger systems, it becomes large deal, right? So it becomes measurable, and that's what takes time. And then there's also this time of putting things into the memory and kicking them out. Okay? So that's how we actually measure speed of the algorithms. So, oh, wrong file. So essentially, I have this forward elimination steps that is O of n cubed, and this O is the order of. And it even doesn't matter whether it's 2 times n cubed or 3 times n cubed, it's the n cubed that is the problem, right? So we're not going to spend time counting small stuff and peanuts, but it's this larger. And then O on n squared, back substitution is O of n squared. I literally go through my for loops, see how many times they execute for the size of the problem. And here we're calling the size of the problem n, right? N unknowns that I'm solving for. Okay? So n cubed type of algorithms, O of n cubed type of algorithms are slow. Okay? And Gaussian elimination is slow. Also, as I pointed out already, in Gaussian elimination, doing that many floating point operations will do a whole lot of rounding up of those numbers, and those errors that we have that we cannot avoid of storing stuff in memory, in finite memory of a computer, will also take toll on the accuracy of the method. Okay? So in that sense, for anything that is really larger than 1,000, we are not going to use Gaussian elimination. Now, I can actually just, to show you the timing, so for those of you who haven't started, what I suggested is to basically go to Spider and not to do Python. So this is just to show you timing of built-in solving algorithms. So this is linalg.solve. I pointed out, and it's on your slides if you need it, that there's linear algebra solvers that are built in. One thing is that right now I didn't look up, whenever you have a canned solution that you use, we actually don't know what method is being used. So for smaller system, maybe it's Gaussian elimination, maybe it's something else. We're going to go to different types of methods that are faster later after this lecture. So there is something that is possibly the fastest possible. And also, a lot of these solvers have been developed literally since 1940s and 1950s. Okay? So they have been optimized over the time. So often when you actually go to a solution that is, there's these codes that are behind that are heavily optimized, and there will be first, like, based on the problem that you give it, it's going to figure out what is the best algorithm to use. So there's a lot of optimization over the time. What we are doing in class is simple just to get the understanding of how to build those algorithms. So right now, I did not go into research what's behind linalg.solve, and most likely there's 4 or 5 methods that linalg.solve goes to, and picks one based on what I give it. So something as best as Python could drum up, okay, is behind this. Now let's see how this best thing works. So I said, okay, I gave myself a for loop. This is a list. So if you remember, I can use that in a for loop. So I just gave a problem of 1,000 by 1,000, 2,000 by 1,000, 5,000 by 1,000, and 10,000 by 10,000. So I create myself a random matrix A in my random right-hand size of n by n and n by 1. Okay? And then I start my timer. I go to whatever it is that I want to time when I want to see how long things take. And I basically say, hey, solve this problem, and just time it. So I'm not looking into how well it's solved or whatever it is, or whether the problem actually makes sense. It's random numbers. I'm just looking to time things. And then you can do the timer. So if you want to time how much time does 9 million additions do, create yourself a for loop that adds something 9 million times, right? And see how long it takes on your computer. Okay? So that's something to have fun with if you want, but you can time anything, and then I print how much time has elapsed. Okay, great. So if I actually executed, and it took about 40 seconds for 10,000. So I'm not going to execute it now, but I executed it just before coming to class. So this is what I got on my laptop. My laptop is nothing to write home about in terms of speed. You might have a better one. So 1,000 by 1,000, it took 0.65 seconds. They blink in that time. It wasn't something that I would be concerned. Then, for some reason, the second one got even faster. Okay. So sometimes it's like, question is, what was my laptop working on in parallel? Okay. I have about 40 things open. So one of them maybe took a little more time. Then in a larger system, it took 3.2 seconds, and then on the order of 40 seconds. Gaussian elimination, I want you to time, and I'm going to report my results together with you by Friday. But this is something that you can, that you're going to be required to submit on the form as well. So that way we can see the range. Again, time depends on what are you asking it to do, what else is going on your computer. It's possibly not working just on that. So that's something to think about. So in vein of thinking of how to speed things up, we're going to work first on an algorithm called LU decomposition. And this LU decomposition, which for some reason, there we go, need to swap this place, is looking to cut down the time needed to solve something. In cases where I'm solving systems where I have AX is equal to B, and A remains the same, but B is changing. And that's going to be a little clear when we actually get to the end of this lecture, when we do the formulation of the system. But this B, so A is often something that is, let's say that I'm solving a physical problem of flow through pipes. What will go into A is basically the physical dimensions of those pipes, or stuff that is related to the physical dimension of the pipes. And what will go into B is basically my boundary condition in terms of what is the flux that I'm imposing, or what is the sort of like something that is coming in and out of this system. So often, basically, there's certain physical description of the system that actually builds my coefficients in A, and it is the current situation or current maybe flow or temperature or whatever that I'm running my problem at that goes into B. So as an engineer, I typically build my infrastructure and then I run it for multiple fluxes, for multiple temperatures, for multiple, you name it, right? So basically all I'm changing is B. In this formulating AX is B, I'm changing B, and I'm solving this AX is equal to B all over again. Okay? So this is where we can try to save some time, okay? And basically do something, this forward elimination step that I'm doing, my A in this forward elimination is not going to change. This step of changing A is not going to change. It's really just what's B is changing. So maybe I can save some of it and cut some of the time down. So that is the idea of LU decomposition. So formally, if I have a problem AX is equal to B, okay, I can, in this forward elimination, I end up with this upper triangular matrix. And I will end up with something looking like UX is equal to D when I do this forward elimination step. Reality is that there is actually a lower triangular matrix that I can multiply this U that I got at the end of here and get A. So my A is actually equal to LU, where L is lower triangular and U is upper triangular. Great. So basically what it comes down to, and we are going to go through that, what it comes down to is that I have to, as I'm manipulating my rows and whatnot, I just have to remember some of those coefficients and put them into L. Okay? And I'll have it. Great. So my A is equal to LU. Okay? So technically, my problem L is, so I have UX minus D, so my problem, actually I have that written a little better here. So my AX minus B is equal to 0, right? And it's actually LUX minus B. So technically I can kind of factor L to the side as a matrix multiplication. So this problem is equivalent to a problem of L times UX minus D. And that has to be equal to 0. So if I actually go and split my A into L and U, which is really doing forward elimination once, then what I'm left with is that this problem LUX is equal to B. So basically, I'm splitting problem to the following. My LD is equal to B. My LD has to equal to B. And my UX has to equal to D. Okay. Since this is a lower triangular problem, it's actually forward substitution. We had backward substitution, there's forward substitution. So it's a relatively easy problem to solve. And this UX equals to D, that's a backward substitution. So I'm splitting things into 3 things. First, I set my A as A is equal to LU, so I find that. And after that, I'm solving LD is equal to B. I find D that way. And then after that, I'm solving UX is equal to D, and I find X that way, and then I'm done. Now, if my new problem comes in with new B, I don't repeat my LU decomposition. All I repeat is these two steps, forward and backward substitution. And that is cheaper because if you remember, these are O of n squared. So 2 of them, O of n squared, is way cheaper than O of n cubed. Okay? When n is large. Okay? Okay. I'm going to switch to writing down, and I'm going to write this down and give an example so it should then sink in. Okay? Yeah, I'm going to hang. Okay. So basically my topic here is LU decomposition. If my if my hardware decides to communicate, which it doesn't, okay, I have a non-responsive screen. I think so. Technology, great when it works. Not so much when it doesn't. Come on. I'm old-fashioned, sorry. I have to stop recording.